Hey guys, so welcome to this talk tonight. I want to give you a quick pitch about a hackathon we have coming up on November 2nd. You guys should all come out. It's a 24-hour hackathon. It's the largest student-run hackathon in Michigan, so you guys should check it out. This is Eric Wustrow. He'll be talking about network tools and finding who to blame. He's a security grad student here at the university, and the stage.
Oh my God. The front one is probably getting it easier to read.
Wow, every light switch.
Probably all that time.
Oh, that's where I would have put it.
Yeah, behind the screen.
Well, it's clear that it operates in that corner of the room.
As long as you have X-ray vision.
Right. So, thanks everyone for coming. I'm Eric Wustrow, as Evan said. So, the title of this talk is a little bit, contrived. But basically, I'm going to be talking about my favorite network tools that I've just, discovered over the years or used over the years, and I use these quite frequently, I guess. What's going on? Anyway, so finding who to blame is sort of a reference to, like, you can use these tools to figure out why your network is broken, or figure out who's to blame for your network being down, whether that be Comcast, your roommate, or the government of China. So the internet, for those of you who don't know, is really about packets. And it took me a while to figure out that I really like packets. Packets are like this really cool thing. Packets are amazing. And it took me a while to figure out why they're so amazing. And the reason that sort of just hit me one day was that I'm programming on my computer. I'm changing the pattern of light so as to XKCD comic code. And I can do that in such a way that I can generate a packet that will get sent literally around the world. I can create a packet just using my keyboard and computer and send it out over the network, and that bit of data that I've generated can actually find its way to China or Germany or Australia or anywhere in the world that's connected to the internet. And what's cool about this is not that this is the first time that we've been able to do this in human history. No, in fact, far from it. We've been doing this for thousands of years. We send ships across the sea with large packages in them, and these would make it away across the ocean. But what's really cool about this is that we can do this in mere milliseconds, right? This would take months and cost lives, and there'd be lots of scurvy and things like that. Now we just wait a few milliseconds and then it's there. But much like the previous networks that we had, our current networks are what we call best effort. So what it means is when we send a packet, we're not actually sure if that packet will actually get there. The network is just going to do this sort of best effort approach to getting that packet to its destination. So the ship might sink, they might all die from dysentery or something, or all of the routers on your path might just drop off the face of the earth. So to solve this, there's a really simple way to solve this, and that is to use acknowledgements. So if we have A trying to talk to B here, A is going to send this message hi, and if we want to make sure that B got that message, we're going to ask B to send an acknowledgement back to A that says, yes, I received your message. And of course, if for some reason this packet gets dropped or this message gets dropped en route to B, then after some period of time, A will know, well, I didn't get an acknowledgement back from B, so I should probably send it again until you get that acknowledgement. And this is the basis for sort of TCP. And I won't go into all of the details of TCP in this talk, but we'll sort of skim the surface of it. And this is sort of the connection handshake, how you set up a TCP connection with a server. So you use TCP for things like HTTP, all sorts of things use TCP on the internet. And the general sense, or the general idea is that the connecting client, in this case, A wants to establish a connection with B. And so A sends this packet, this SYN packet we call it. And this is just a packet with a special field set. And if B is accepting connections, B will send back, well, after it receives that connection, or after it receives that packet, it will send back a SYNAC packet. And this is just saying, yes, I would like to also start a connection with you, or yes, it's okay to start a connection with me. And I'm acknowledging your first packet. And finally, A is going to acknowledge this acknowledgement. So you might be like thinking, well, wait a minute, shouldn't we be just acknowledging these back and forth? No, it stops there. We're done after this third part of the three-way handshake. And as it turns out, if this last act gets dropped, then the SYN act will get resent, and eventually it will go through. So that's sort of just the basis of TCP. And you've probably heard this a million times in all of your software courses and things like that, but you may not have actually used it using a command line or using a program or something like that. So let me just stop here and demonstrate one cool tool that can be used to do this sort of thing, which is netcat. So, can everyone read? Oh. This will work. This will work.
Great.
Yeah. All right. We're good. Yeah.
See, it just worked.
So who can read this? You guys can read this? Yeah. All right. Great. So netcat is basically a tool that allows you to create TCP connections on either side, listening or connecting, and it's a great little tool. So how you use it? It's just NC, and it's the netcat. And so on this side, I'm going to just listen, and I'll just pick a port. So -L, pick a port, and I'll just hit enter. Great. So now I'm listening. And on the connecting side, I'll just do connect to that. And so now I have these two things connected. It didn't say it because I didn't use -D. But if I type in this window and enter, it gets sent to the other window. So this is a really basic example of what's going on. This right screen made a TCP connection to the left process in this example, and the left process accepted it. And we were able to send over some data, and it got acknowledged because this is all TCP. And so we get to see at the application layer what's going on here. Also, feel free to interrupt me with questions at any point in this talk, because it's sort of just going through lots of tools and things like this. This is a basic tool, but yes, you have a question on it.
Why 207.0.0.1 is the local host?
Yeah, so this IP address that I typed in here is my computer wherever I am. So this is localhost. This is true of your computer. Your computer is also this address, according to your computer. It's a way to refer to yourself. And in fact, any address starting with 127 refers to yourself, not just 127.0.0.1, but we use that one just for convention to refer to yourself or local.
How did people come up with this version?
So you might be wondering, wow, that seems like an egregious waste of internet address space. 127/H for talking to whatever computer you're on. And I would agree, that's probably true. We're kind of running out of them, or we are out of them according to who you talk to. So we should probably fix that, but legacy systems, we will never really be able to fix that, so this will probably always just be So the reason for why is because when it was first chosen, we had that much space. We thought we would never run out of IP addresses, or we just thought, why would the internet grow that big? There's only going to be like 5 computers, right? We'll be good. I'm really happy that no one discovered my IP address before I did and connected to me. That would have been a good trick.
A pretty short window of time. There's big wireless search over here.
That was on purpose. So another cool tool that you can that I can just show you real quick is that if I do netstat, I can actually see these connections. I should have done that in a better way.
What window manager are you using for your shell? Because I wanted
Terminator.
It's not a window manager, it's a terminal manager.
It's a terminal manager. It's called Terminator, and it was suggested by my advisor, Alex Holland. So he's very happy that I'm using it now. So in netstat, we can see 3 things. We get to see, 1, there is someone listening on port 1337, and that's this process. And the IP address that it's listening on is all zeros, which means that it will accept connections to any destination. The second 2 correspond to each of these processes' handles on the connection between them. So if I were to connect to a remote host, I'd only have one of these. But since I connect to myself, I get to see both of them. And so you can see that these are symmetric examples of each other in this instance. So that's the basics of netcat. What can we do with netcat? Well, there's a lot of cool things we can do with netcat. Let's just start doing them. So one thing you can do is you can connect to a web server, and you pick port 80 because we're going to talk HTTP. So I just pick google.com, port 80, connect to it, and I just start typing in HTTP. 1.1, I give it a host. And that's all you really need for an HTTP request. So that was cool. We got Google to spit back to us a bunch of HTML, which is impossible to read because they like to just pack it all over the place. But so that's one thing you can do with netcat. But another cool thing that you can do, which is even better, is you can do you can connect to mail servers. And mail servers will accept, generally, they're misconfigured, will accept anyone connecting to them and sending emails. So then we can do things like mail from the president at Kenya. I didn't realize this doesn't work from wireless. However, wait for it. Wait for it.
Might be.
There it is. Good. Now we just send some data, and we can just say, well, this is from President at whatever to Eric. And subject, what should our subject be?
Asbestos.
Then we'll just say, dear sir or madam, I have 1 million. You have a bank account. Great. Send that, and the message is delivered. Okay. So now just to verify that that actually happened. Okay, quit. Oh, that's a tab. Quit. Yeah, all right. So now, if we go to my email, we have an email from the president. All right, so you can do that. I will warn you, though, if you do that too much, or if you get caught doing that, you can get in a lot of trouble. So you should, only do it to yourself or your friends under their consent. Don't use this to email mailing lists that you are not a part of some entire dorm or something like that. That would be sick. So you might have noticed, or you didn't notice because I didn't do this, but if you had root on my box and you did this, or you were just watching because you were a user on my box, and let's do local port on google.com port 80. What's dash P? Dash P specifies that I'm going to listen, I'm going to use that as my local port. I'll show you in a second. That's that dash 10, correct. So when I connected to Google, I used local port 1111 instead of just an ephemeral port or a random port. And so you can obviously see here that I'm not connected to google.com, I'm connected to some IP address that happens to be google.com. And for those of you who know how DNS works, this is easy, but come on, how did we get from google.com to this IP address? Well, to answer that question. Yeah, all right. So how do we get from a domain like merit.edu to an IP address, google.com to an IP address? And it turns out the answer is DNS. But it used to be actually a much simpler answer. It used to just be that you had a file on your computer that mapped domains to IP addresses. And if you had this file, then you were able to map merit.edu to this IP address. And if you didn't have this file, you weren't able to do that. And so everyone just shared this file. We called it the hosts file, and we shared it around widely. And then that turned out not to scale so well because everyone was like, well, look, my IP address changed. And someone would say, well, but I want to add one now. And no, wait, that's my domain. You can't take that. So there was all this bickering. So the overlords of the internet decided that they were going to create this hierarchy. The overlords being IANA and ICANN. And they said, look, we are sort of the authority on the internet. We're going to control, we're going to sort out who owns what domains and all of this stuff. But they did it in a really clever way where they didn't actually have to do any work at all. It was really brilliant on their part. They were able to control the internet without having to do any work. So what they did was they said, how about, well, let's set up a bunch of top-level domains. We'll call it .com, .net, .us, all these different things. Everyone, you can come to us and you can try to convince us that you should have a TLD, and we'll say yes or no. And if we say yes, then what we'll do is we'll add the whereabouts of your root server at our root, at our server, which we will call the DNS root. And so now, if everyone knows where this DNS root is, they're able to ask us, hey, who should I go to talk to if I want to figure out the IP address for google.com? And the root guys will say, oh, well, I don't know, but I'll bet the .com guys will know who owns that IP address, who owns that domain, and will know the IP address for it. So you should go talk to them. And so there's this sort of hierarchy that's going on, and I'll walk through an example of this in just a second. So everyone in the world knows where these root domains are. They know the IP addresses for them because it's just hard-coded in your computer. It's hard-coded in the recursive resolvers that we're going to use to look this up. So from your perspective, you just talk to a recursive resolver that's on campus or level 3 or whatever. You found an open resolver in China and you think it's funny to use, and that's great. So you just talk to that recursive resolver, and it gives you back an IP address magically for every domain you visit. You ask it google.com, it spins for a while, and then gives you an IP address. But really how this is working is that recursive resolver is doing a lot of work. So if the recursive resolver is just booted up and doesn't know anything, the first thing that it's going to do is contact the root server. And so in this example, we're looking up my domain, ericw.us. And so it's going to ask for what we call the A record here, which is the record that corresponds to the IPv4 address for this domain. So this recursive resolver will just send this query. Hey, I'd like to know the IPv4 address for ericw.us. And the root server, just like a good bureaucrat, will say, I don't know. That's not my business. But I know who might know, and it's going to point us to the .us top-level domain. And it's going to say, don't know about ericw.us, but .us, all .us's, are in this name server, a.cctld.us. Now, if it were not a nice name server, if it were not a nice root server, it would not give us this additional field here, and we'd have to do an extra lookup. But that would be really neat. So it will actually tell us the IP address for this next thing, so we can know where that is. So now that we know where that is, we're going to go, okay, now we'll ask this guy, this .us guy. Surely he knows the IP address for ericw.us, because he's the .us TLD. But he doesn't. He actually only knows where the name server for ericw.us is, which happens to be some zone edit, which I've sort of simplified here. And so we will further ask that name server, what is the IP address for ericw.us, and finally it will tell us an answer, which is the correct answer. So there's this whole sort of chain of delegation going on in DNS, which is great and ripe for all kinds of attacks and things like that, which I won't get into in this talk, but we'll get to do some fun things with it. So if we go back to getting better. Yeah, all right. So there's this cool tool called dig. And dig is what allows us to look at these DNS records for arbitrary domain names. So we can see things like, okay, I'm going to dig google.com. And that will give me a bunch of IP addresses, actually. So you can see here, our question section was google.com, internet A. We're looking for the A record in the internet class for google.com. And the answer that we get back from our recursive resolver, since we didn't actually do the work, we just get the answer, is actually 11 IPs that correspond to google.com. This is a way of doing load balancing right here, is that your browser will pick one of these to connect to, and if it fails, maybe it'll go on to the next one, depending on how it's feeling that day. So So you can see that we can dig just basic domains like that. We can do even better than that. We can actually do plus trace, which will actually do all of those steps that I told you that I just told you about, where we ask the root what's the IP address for I'll look up ericw.us just for fun. And I'm just providing some extra flags, so it gives us a little bit more information than it would otherwise, because it's kind of sparse. So, as you can see, we went to the root, and we got the root servers, and we got their IP addresses. And then we asked one of them, ericw.us in A, and it told us, don't know, but US is in name server one of these guys, and here's the IP address for it. And so then we went and asked that guy, ericw.us in A, and it said, don't know, but the name server is name server 13 zoneedit.com. And so then we asked that guy, and finally he said, yes, here's the IP address for ericw.us. So dig is a pretty cool tool. This will allow you to tell if your DNS provider is down or something like that. You can also choose to dig at specific name servers. So for example, you can dig at 4.2.2.2, which is a name server run by level 3, and it'll give you back answers. But if you dig at something that doesn't exist, then you won't get an answer. However, and here's a good trick. So dig at something in China. So Baidu.com is in China. And if we dig for Google.com, we won't get anything. But if we dig for Twitter.com, we'll actually get a response. And this response is actually wrong. so if you actually dig for real Twitter.com, find that the real response is these 4 IPs with a TTL of something like 30 or something like that. It should be 30. And so, but if we dig at something in China, we'll get these lies. And we'll get different lies every time, every so often. It's a different lie. Lie. It's not playing. Oh. Yeah. Okay. I see what's going on. Yeah, there we go. All right. So we get a different lie every so often from China. It's just going to lie to us. And what's actually going on here is that they do this censorship at the edge of their network. So whenever a DNS request leaves China for, say, Twitter.com or Facebook.com or something that they've blocked in China, the edge of the network will actually spoof a response as if it came from the real name server back into China. And this is really clever because it actually turns out that this will infect or poison the caches of recursive resolvers in China rather than having to respond to every client in China that does a DNS lookup for Twitter.com. But it also has the side effect, if we dig from the outside into China, that we'll get these spoof responses, even in the case where we wouldn't get a response at all. Yeah?
So the network does kind of have this top-down hierarchy, but there is a lot of distributed element to it. So what's stopping them from getting add-on networks? They just start copying in and adding extra connections out to the outside world through other links, through satellite links or whatnot.
So what stops citizens in China from using satellite links?
Or just hooking in their own name resolvers in different networks in this area, and basically forking off parts of the network away from the main centralized control locations.
So for China specifically, all of the network infrastructure at the ISP level is owned by the government. So it's all state-run for the most part. So there's not really going to be an ISP that decides to do this. It would mostly just be citizens or activists or something like that. And they do this. They use proxies. They use Tor. They use telex. They use all kinds of different proxies to get out of the country. But yeah, I mean, it's sort of, it's not happening at a huge scale. It's happening at an individual basis. Yeah.
So if they just type Twitter's actual IP address into their browser, would they get to Twitter, or would it block them still somehow?
So if they type Twitter's IP address, they actually get IP blocked. They actually also IP block Twitter. So China is doing IP blocking. It's doing deep packet inspection. It's doing DNS filtering. And depending on how angry it is at a particular site or how much it wants to block it, it will do some subset of those things. So when we were first doing experiments with China, we got DNS blocked by that. We had the domain notblocked.telex.cc, and people were using that, and they just decided to do this DNS spoofing for not block.telex.cc. So we started as a joke, not really block.telex.cc, and we started running this, and they caught on like in a day or so, and they DNS blocked that, and then IP blocked both of them. So they were like, we're not playing this game anymore. IP blocked. I assume that they do. The reason that they don't just IP block and call it good is because Twitter changes IPs just on its own every so often, just because it has lots of IPs that it wants to load balance between and so forth. So DNS sort of provides this extra layer of protection for them. Yeah.
What stops your Argent US citizen attending overseas at or the affiliate university in Shanghai from setting up their own name server reservables for all their friends and whatnot, and they're piping through the VPN?
Sure. So you can set up VPN, you can run services and name service and stuff like that until the Chinese notice it, and then they're like, hey, what is this? It's running in our country. Maybe they'll like send a guy out. Who knows? You know, they've got hidden jails. If you want to play that game, that's up to you. No, but some people do this, and some people are activists about this, and that's cool. But you do have to realize that there is some element of risk of doing that sort of thing when you're in a country that's as oppressive as that. All right. Yes. All right. So another cool thing that you can do with DNS is this thing called iodine, and this is a tool that basically takes your traffic and tunnels it over DNS. So say that you're at, I don't know, an airport with Starbucks, a Panera, or something like that. I don't know, something general, where you only have DNS access. You have DNS access until you pay for internet or something, or anything like that. And I'm not suggesting you do any of this, right? Something you could do. So what iodine is going to do is, because you don't have IP traffic, you only have DNS traffic, what it's going to do is it's going to take your IP packets that you would normally send out over the wireless interface or over the IP layer, and translate them to some string. So in this case, this is just some readable string, and append to the end of that some domain that you control. So in this case, a.ericw spelled incorrectly. So we're going to take that domain, and we're going to basically just do a lookup on it. Now, what's going to happen when we do this lookup on it? We're going to send it to our local resolver, and our local resolver is going to do the whole thing that we did before. It's going to talk to the root. It's going to say, I don't know, go ask the .us. We're going to talk to the .us. Let's follow it from there. So we're following it from .us. We ask, what's the IP address for this mess.a.ericw.us? And it's going to say, of course, I don't know, but the name server for a.ericw.us is ericw.us. And by the way, here's the IP address for ericw.us. And our friendly local resolver is going to go and talk to ericw.us, which, by the way, is owned by me. It's running in a cardboard box. It's great. And it's going to send this record to ericw.us. But of course, this is my server. I saw this coming. Right? I have a program running on my server that's going to take this request, say, aha, I know what game someone's playing, and say, take off that first bit and turn it back into a packet, and then send it out to the internet. So now we've basically taken our packet and we've tunneled it over DNS, gotten it to our external server, and now that has sent it out onto the internet on our behalf. Now how are we going to get data back from the internet? Well, if the internet sends us a packet back, it's going to send it back to ericw.us because we're doing some kind of proxying here. And what ericw.us is going to do is it's going to retranslate that back into a CNAME in this example, and just stuff that back into the response of this. And so me, as the person sitting in Starbucks or whatever that's not paying for internet, is doing is just sending out these requests and getting back these responses. But really, the requests that I send out are IP packets that I'm sending out, and the responses I get back are IP packets that should be sent to me. So it's a really clever system. And I'll just demo how it works briefly. All right. So we run sudo iodine because it likes to be root because it's going to create a new interface. We run iodine. -r -m to make it faster. So same domain that I was just talking about. Right, so now we've created this DNS0 interface, and we can ping the other end of this interface, which happens to be this address, which normally I wouldn't be able to ping, and I can SSH to it with some socks proxy. One. And this is an SSH connection going over DNS, and there it is. It's a bit slow. It's not the best in the world, but it's pretty good. You know. Oh. All right, we're just killing that one.
What's the legality of this?
So the legality of just doing that is, as far as I know, and I'm not a lawyer, I would say that that's, you know,
Consult an attorney.
right. But honestly, I can't see. I mean, I'm doing this over my own. So the only thing that is involved in this that's not mine is the recursive resolver. And so perhaps the U of M could get upset that I'm doing this recursive resolving and sending all my IP traffic over this recursive resolver.
One place to figure out a hotel thing is.
Consult an attorney. Yeah. All right. So any questions? Any other questions up till this point about iodine? Yeah.
So if you're doing that, it gets like prefixed as pretty much a subdomain. So does it do anything to prevent collisions with a subdomain? Like what happens if you request a packet and you have to have the subdomain like development.a or
Oh, so yeah. So I specifically use a.ericw.us so that I don't collide with anything. So everything below a.ericw.us is just for iodine use, basically, in this domain. And so, yeah, you shouldn't have collisions. Otherwise, yeah, you're going to have to do some kind of collision resolution on the server side. But you shouldn't run into that one yet.
Does DNS have max packet sizes that you'll like
yes.
try and port it through somewhere it's going to explode back at you saying sorry too big basically?
Yes, in fact that's what iodine does when it first runs, but I skipped that step because it takes like a minute or so to run. But basically it's going to just binary search out the maximum request that it can send and the response that it will get back. And that happens to be on this link 1,152 bytes. Yeah. Maybe.
What are the security implications for you doing this? Like, can other people see what your DNS queries and that?
Right, so people can see your DNS queries and they can obviously get your IP traffic from that. So that's why the first thing that I do whenever I play with this is SSH to a domain I control. So now everything that goes over that tunnel is going to be in an SSH tunnel, in a DNS tunnel, over IP. Right. So if you're playing at home, it's IP over SSH, or over socks, over SSH, over DNS, over IP. And yes, you can make this loop many times. It's kind of fun to just do like iodine over SSH, over iodine, over SSH, over SSH. You can do that as many layers as you want, turtles all the way down. It's great fun. Any other questions? All right. So the next tool requires a little bit more background as well. And it requires a little bit of knowledge about how packets actually get from point A to point B. So in computer science, we can usually abstract away this problem, but I think that this is a really cool part of the internet, and unfortunately I won't get to go into all of the details of how this works. But from a simple view, the internet looks like a mesh of interconnected nodes. We call these routers. These routers are, in this example, red, and there's only 5 of them, but it's a very simple network. So what we're going to do when we send a packet from A to B is A is just going to send this packet to whomever she can send it to. And in this case, that's just J. Now, how does J figure out who best to send this to? It turns out that no one here actually has this global perspective. We're giving you this perspective as a benefit here. But none of these routers really know the full map of the internet. They just have sort of a sense of who's around them and maybe they have an idea of which direction B is in or something like that. So it's sort of like the delegation, but it's sort of like a more local form of delegation or a distributed form of delegation where you're just like, I don't really know where B is, but I'll bet K has a better idea of where B is than I do. It's sort of like if you're in a really crowded theater that's, you can't see all the way to the edges or something like that, and you want to send a message to your friend, you know he's over in that direction. You'll just start telling people in that direction, hey, pass this message along, and eventually it might get to him. Like I said, best effort, it might not get to him. So in this case, J is going to send this message to K, K is going to send this message to L is going to send this message to M, and for whatever reason, M is misconfigured or hacked or whatever, and it's going to send it to N. Maybe he's confused the interfaces or he's just having a bad day. And N maybe knows this, or maybe he doesn't. Maybe he's also misconfigured. N's just going to send it to L. So now we have a problem. L has received this packet before, and he sent it to M. So he's just going to do the same thing that he did before, and this packet is going to go around in this loop forever. So this is a problem. This is called a routing loop, and this happens in the real world. This happens because of misconfigurations. This happens because the paths that you send the packet out on and receive the packet back from are not always symmetric. It happens for all kinds of reasons. And it's actually going to get worse because as this goes around in a cycle, A is waiting for some acknowledgement from B or something like that, and is not going to get it. So A is just going to send another packet into this routing loop. And so there's going to be more packets in this routing loop. And this will never terminate. But network engineers thought of this, and they said, well we can think of a number of solutions to this. We can have L keep track of all of the packets that he's sent in the last 10 seconds, and if you see another one, just drop it or something, but that seems messy. So what they decided to do instead was add this thing called a time to live. And how this time to live works is you basically just staple onto this packet a number that tells you how many routers this packet is allowed to go through before you should be worried and drop this packet or something because you've probably encountered a routing loop. And we can set this to some reasonable value because we know what we call the diameter of the internet is roughly about 20. That means when you send a packet from one host to another, no matter what host you pick, at most you'll probably go through you'll go through no more than 20 routers on the way from point A to point B. And so if we set the TTL to something a little larger than that, say 64, or in the case of like Windows 255, they didn't really care about the diameter of the internet, then this packet will go until it reaches that many routers. And if you hit a routing loop, as we'll see in a second, so we're sending this packet, every router has to decrement this TTL. So this is sort of the disadvantage of this scheme, is that every router that encounters this packet needs to unstable this TTL, decrement it by 1, check it at 0, and if it's not 0, forward it on. So in this case, J decrements to 8, K to 7, L to 6, and we're entering this routing loop, but it's okay, don't worry, because when it gets to 0, when L decrements this TTL to 0, L says, aha, that should never have happened. We should throw out this packet. So first it kills the packet, it drops it on the floor. But because L is also a nice router, it's actually going to notify the sender. This is sort of like the post office does if it can't find the address or something that you're supposed to deliver it to. It's just going to send what we call an ICMP message, which is just a control message that sort of is used to communicate between routers and clients on the internet to communicate things like this, like the fact that your packet was dropped because this TTL ran out. And what's really cool here is that L will actually send this from the IP address of L. So A actually learns which router this got dropped at. Yeah?
What happens if you have a bidirectional loop that happens where it'll try and bounce the packet back and forth?
So then you're not going to get it. But, so that's the reason why we don't send it to B, is because in a unidirectional loop like this, or in a loop like this, you wouldn't want to send messages to B because clearly there's something wrong with sending to B. But yeah, in the case where you have a bidirectional loop or something in both directions, loops, A is not going to get it. But usually that doesn't happen. Usually it's like you'll get it in this loop somewhere for sending to B, but sending to A is fine or something like that. Yeah.
So my point was like when the packet expires though, L will generate another packet. It'll then also get stuck in the loop, and this will continue on forever.
L is sending this packet to A, not to B.
Okay. Well, what if you get into a loop where it can loop back into this network, and then you can't get into a loop happening?
Then it'll send an expired to L.
Yeah.
And
yeah.
Right, which it can get to.
Right. Okay. Then it will send it. Yeah, exactly. So this should not result in packet explosions or what we call loop floods or broadcast floods, depending on how they're generated. If it does, you probably have something much more serious wrong with your network that this is not going to help diagnose. And you'll notice because you just don't have internet or something. So yeah, so A now knows which router this packet expired at. So we can play this clever game. We're going to call this game traceroute, or map the internet. So A wants to know all of the routers between A and B. And so the first thing A does is A sends a packet to B, but arbitrarily sets the TTL to a really low value, like 1 here. And so when J gets this, J's like, oh, that's weird. I got a packet with TTL 1. Decrement it, oh, now it's 0. Well, I better drop it, and I better send A a message that says that you had exceeded TTL on my router. So now A has learned the first hop in this connection to B, in this path to B. And so we can play this game again with a TTL of 2, and of course now we'll learn K, and we can play this game basically all the way until we actually get a response from B. So we will know exactly how far B away is, and be able to figure out all of the routers in between. And it turns out that there's actually a tool that we can use to do this called traceroute. And you may have used it before, you may not have, but here it is. So you just pick an endpoint that you want to traceroute to, and voila. It's going to send a packet with TTL1 and see who responds to it, and then we do a nice little reverse DNS lookup to get a nice name instead of just an IP address. And we will also ping that IP address to give you a round trip time for that host. And so you can see that these round trip times are increasing as we get further away, as you'd expect. As you get further along this path, it should probably take longer to send a packet to that router and get a response back. And so this is kind of cool because you can actually follow what path your packet would take through the network on its way to, for example, Google. And this is a really bad example because Google doesn't label their routers very well. So at the end here, we're not really getting any information other than just IP addresses. But you can follow it through U of M. We go to Arbor Lakes, over Kane. We go to the basement of the School of Education building on Central Campus. Then we go down to Michigan, which happens here with, I think it's also in the School of Education building. This is in Chicago, so we've hopped all the way over to Chicago now. And then at that point, I think we're peering with Google somewhere in Chicago, and the packet reaches its destination a mere milliseconds later. So 10 milliseconds we're in Chicago, 11 we're at Google. Yeah, probably not that far off. Yeah.
So you said it normally increases, but why is there places where it decreases?
So sometimes it will decrease, and the reason for that is sometimes, well, so there's a few reasons, but basically one reason that is really common is that routers will sometimes prioritize ICMP messages, which are the ones that need to respond to these pings. So they'll have, so a router will have high priority for IP traffic, for example. So it'll route IP traffic really fast, but it will route ICMP messages much slower. So if it gets an ICMP, it'll be like, I'll deal with that in a few milliseconds or something. So for these routers up here, that may be the case. And so they will inflate the round trip time artificially in that case, when really it's something more like 2 or 3. And also there's just noise, so if you run it again, yeah, so if you run it again, now it's a little less, although it's also but this gives you a general sense of sort of what's going on. And you can trace out some other cool things. So this is another host that's in China. And yeah, so this one's kind of cool. So this one goes same as we did before. We go to Chicago, we reach Internet 2. Oh, RenRen's not responding to my pings now. All right, we can play that game in China. And so we go to Chicago, and then we jump on the Internet 2, which is sort of this U.S. network that is for research institutions and things like that. It's really, really fast, and they have like, well, it used to be really fast. Now it's just kind of like as fast as the rest of the internet, but it's still pretty cool. So here we went to Chicago, we went to, where is that? I think that's Washington, D.C. Let's do
Palo Alto?
So yes, it's so Palo Alto is like what PAIX is, but yeah, I'm not sure if that could be Palo Alto actually. let's do sjdu.edu.cn. Do a research university in China. So yeah, so this one, okay, yeah, you're right. So here we went through Wayne State University. Oh, sjdu is not responding. All right. So we went through Wayne State University, we went through Washington, D.C., we went through Atlanta, we went through Houston, Texas, and then this is probably somewhere in California or close to it, and then this is across the Pacific Ocean. So you can see there's a huge jump here, 88 milliseconds to 232 milliseconds. So we've clearly left the continent here, and this is reflected in the round trip time to these servers. Yeah.
I know, like, speed of light time to geosynchronous and back is about 200. So is it taking probably a satellite jump then?
It may be, actually. I'm not sure, but I think most of the traffic to China is transoceanic cables and stuff like that. So. And I have found some paths that sometimes this path will actually go through Germany in the other direction. So we'll go across the Atlantic, Germany, and then into China that way. So it's actually kind of cool because, you know, and it will pick this based on, the network will pick this actually, you don't get to pick this, but the network will pick this based on what routes it sees is up or what it sees is the best route at that time. Yeah.
Between those first two 210 IP addresses, which I think are both in China, there's like a 150 millisecond jump. Is that because they're doing some sort of filtering there that adds a delay?
No, most of that's just geographic latency.
Those IP addresses are almost the same.
Yeah, so the reason for that is because this is an exchange point probably on the US side of it, and this is the exchange point on the Chinese side of it.
They own by the same
So they can be owned by the same network, but they're on completely different sides of the continent, right? Because you're not going to have you're not going to peer with China in the middle of the Pacific Ocean. You're going to peer on one side, right? And so what it means to peer is that you'll have two IP addresses that come together. One of them is owned by one party, one of them is owned by the other party. And so in this case, I think we're just seeing the IP address owned by the Chinese party on the US side of the connection. Does that make sense?
What's the other gap between like 16 milliseconds and 70?
16 milliseconds?
4 and 5.
Internet 2.
Going from Washington to Atlanta.
Yeah, so this is Washington to Atlanta, Atlanta to Houston.
Big increase in 15 to 70 is what you're saying.
Oh, yeah, that's because we went from Washington, D.C. to Atlanta. I mean,
It's not very far. Is that Washington, D.C. or Washington State?
it's Washington, D.C. So yeah, so now it's lower. So you can see now it's 30, now it's only 15 milliseconds.
Probably good work.
If you trace route to ETH Zurich, you get clean names all the way. They're ETH Zurich, ETHZ.ch.
Europe. I don't like
All right, you get ETHZ.ch. Z. Nope.
Oh, we want to. Don't do it. Don't do it. All right.
No. Just Z.ch. Just Z. Yeah. Oh yeah.
Do you?
Well, that's where it gets there. That's the gateway router of ETH Zurich.
Oh,
I
very
don't let
good.
in there.
But I'm in Switzerland in like 3 hours.
Look how efficient that European connection is compared to the Chinese connection. I don't know what do you want
Yeah, for sure. But yeah. Yeah, so you can see clearly we went across the Atlantic Ocean from Washington, D.C. to
Somewhere in France or Germany.
Germany.
Could the slowdown be like a DC ended
Frankfurt.
thing?
Yeah, there you go. Frankfurt.
Just people watching traffic that's headed for China. Like why? Like it just seems odd to me that the initial thing would be that long. And what sort of like? I know that you don't necessarily know anything about this.
Yeah.
But, yeah.
Well, so I don't think that a gateway. So first of all, the gateway that I'm pinging in Washington, when I ping it, it doesn't know, unless it's doing a lot of extra stuff, it doesn't know that that ping corresponds to a trace route in China. Because how the trace route works, which we'll see in just a second, is I send out a bunch of these probes that I described before, the TTLs, and then I get back all the responses, and then I ping those responses. So the second pinging of those responses is sort of like unassociated in some ways, unless you're like paying attention and remember that these probes also go through. So most of the lag that you'll get is like what I said with the ICMP deprioritizing, where you're just like delay ICMP or drop ICMP more likely.
Take my example for a while.
Alright, sounds good. So there's another cool tool that you can use that is basically just traceroute run in a while loop, where if you want to figure out which hops are causing problems, it's just going to run, it's called my traceroute, and it's just going to run traceroute to that same host a bunch of times, and eventually you'll get package drops. And like I said before, these packet drops might not correspond to that router being like overloaded or full or something like that, because again, this is based off ICMP messages, which can be dropped unnecessarily. But you can see here that pretty much right away, once we enter China, at this 300 millisecond hop here, we're already getting packet drops, about 3%, 2%. And you'll see packet drops after that if that's actually true. Because, of course, if this guy's dropping packets, he'll drop packets for the rest of this. So it's a little bit hard to read, but yeah.
Can you just drop packets?
Yeah, wireless will drop packets. You know, let's see. This is much better to do if you're over an Ethernet interface than over a wireless interface. But I have done this from an Ethernet for like half an hour and gotten a pretty nice graph of high packet drops right at this edge here. Because they are doing deep packet inspection there, and it is a bottleneck for their network. So, yeah. Cool. So another tool that we can use, and I'll just go through this one real quick, is tcpdump. You should know about this, but it's important. So tcpdump allows us to actually look at the packets that we're sending or receiving or anything on our computer. Basically, we get to look at an interface. We give it -I, we give it some interface, so I'm going to give it the wireless interface, and we can give it some other parameters. So say we want to, look at a specific host or something like that. Do that. So this, and then say we want to like traceroute that host. So we can see we tracerouted that host. We got our traceroute like we did before, and if we scroll up here, actually, what I wanted to do. Run this with the -V, because now we get more information, more verbosity. And there. So you can see that we sent out these UDP probes to 4.2.2.1. The first one we sent out had TTL1, and we actually send 3 probes per hop. So you can see 111, 222, 333. So you can see these TTLs that were going up. And these are our probes. So you can actually see how traceroute is working using tcpdump. All right. We'll get back to I guess I should do one more thing with tcpdump. So tcpdump can also save to files or later doing. So if we say like, we're going to do that netcat example that we did before, go Pat go. All right, so what I really wanted to do was that and that. All right, so I established a connection. I'm writing these packets out to a file, and now I can view these later. I can actually view these with tcpdump, or I can view them with Wireshark, which I have aliased to change into a new user, which I highly recommend, or use some kind of app armor, because I'm going to get this to show. No, that won't work. Close enough. All right, so I highly recommend you don't run this under your own user, because Wireshark just has O days left and right all the time. Because literally what it does is looks at network packets, runs any one of like thousands of arbitrary just dissectors on that network packet, and hopes that none of them buffer overflow and run arbitrary code that's contained in that packet. This goes wrong all the time. And in fact, there's some pretty cool examples from DEF CON Capture the Flags where people will just throw out Wireshark ODAs to keep people from watching their traffic while they're doing these Capture the Flag. It's a lot of fun. I have a few just in my back pocket, just in case. It's good to have those lying around. Anyway, so this is a
Do you run it as a very unpublished user?
yes. So we can filter on this connection here. We can follow the TCP stream. And we can actually see the data that got sent over the TCP stream. That's the thing that I sent. And you can see here the SYN, the SYNAC, and the ACK that starts this connection. And then a few seconds later, you can see this push ACK. And this is a really nice interface because you can actually drill down into each of the different protocols and look at, let's say, the time to live, which was set to 64 here, or you can scroll down and go all the way to the data layer and actually see how much of the data that got sent. There it is in hex. There it is hex dump. It's LOW with a line break at the end of it. So, yeah. Okay, so I have two more quick tools, which I just want to share with the class. So the first one is nmap. You may have used it. This is legal, I swear. Nmap, what it does is it's going to just pick the 1,000 most popular ports that it has found over the years of port scanning, and try to, given a host, in this example, google.com, try to create a connection to each of those ports. So it's going to try port 80, it's going to try port 443, it's going to take forever because I'm on wireless. Why didn't it like that? Am I online? Let's see. I'm not online. Right.
I'm innocent. I did nothing.
I was going to teach netcat.
Do you still have your iodine interface up? Is it picking the wrong interface?
No. Is Kane down for anyone else? Oh wait, I want to do this, sorry. 192.1. Okay. It's just D. Yeah. We'll call that wireless drivers.
Been there, done that.
Yeah.
Yep.
My Max also.
All right. Yeah, we're back. Sorry about that. So, where was I? Nmapping. Nmap, google.com. So like I said, this is going to send a SYN packet, like we talked about before, to each of the ports that we care about. And if we receive a SYNAC back, then we'll call that port open. If we receive nothing back, we'll call it filtered port. And if we receive a reset, it's basically like go away, we'll call that a closed port. And so in this case, we got only packets back for port 80 and port 443. And as you would expect, if you go to this port 80, at google.com, magic. So you can unmap all sorts of things. You can unmap, this is just telling it, don't care if you can't ping the host, it's up, I know it's up.
Crap.
So we can unmap the login server.
As long as they don't break anything, how safe is it to ping university resources and do things?
So I think so. Looking for vulnerabilities is questionable in a lot of ways. We should consult an attorney. But as far as like just scraping the surface, port scanning just for doing port scans, and nmap can do some pretty aggressive port scans. So for example, I was going to show an example of nmap scraping the internet for configure hosts because it can do that. It can actually like scan the internet, find who's listening on 445, try to exploit the same exploit configure was up to the point where it actually infect the machine. And if it can do that, then it's like, yeah, that host is infected with conflict. But that's kind of unethical in some ways. There's like two flags, safe equals 1 or unsafe equals 1. And if you set unsafe equals 1, it will go pretty far and you probably should not run that one. But if you run safe equals 1, then it's a little bit more passive. So it really depends on what you're doing with nmap and what you're doing with the scan. But you should be aware that you shouldn't really be like running things on other computers without the computer owner's consent, right? And so just nmapping, just doing simple port scans, I personally don't consider that running something against their consent. If they then notice you doing that and say stop, you should stop. But I don't think there's any kind of ethical problem with doing this. And I haven't gotten any kind of trouble for scanning university stuff like this so far. And if you're really worried about that, nmap something not in your jurisdiction. So
What's this?
this is North Korea. All right. That's a sample of 1/4 of North Korea's ID address space. Right? So they have something like 10, 15 hosts up times 4. Yeah, they have about, yeah.
Are we sure all North Korea IP addresses are actually owned by North Korean or government organizations?
So this is.
Who else gets internet there?
Well, that's true, Rob. Like, there's IP address rearrangement going on all the time, so.
So Kim Jong-un is one of these, I'll bet. There used to be a mail server here running a pretty vulnerable version, and before I got around to like actually exploiting it, I think the CIA got to it or something. It's no longer on, but that was a good joke for a while. From here, they actually run a lot of news stuff, so they run like some of these are propaganda websites. This is a propaganda website. I mean, yeah. I have it in English too. Yeah, it's English. They tell you how great North Korea is, why North Korea is the best Korea, and so forth. They actually have a school of computer security experts that they train to hack other countries. And this is like a documented thing. It's pretty interesting. Reading on the Wikipedia article like that.
They get to learn about nmap too.
I'm sure they know about nmap. Maybe they'll even watch this talk, although I don't know Korean. So I want to wrap up with one last tool, which is a really cool tool that I sort of discovered late. I don't think it's a very well-known tool. It's called HPIG3. So what I'm going to do with this tool, this is basically an arbitrary packet generation tool. You can generate lots of packets. You can generate UDP packets, TCP packets for arbitrary ports using arbitrary sequence numbers. You can spoof from other IP addresses if you want. And so I just thought I would just run a quick demo. I'll pass not paying attention. All right. And then all right. So now, first I'm going to cheat. And tcpdump, so we can see the thing that I sent across the wire here. So you can see there were two packets here. There was the data packet that I sent, and there was the ACK packet from the server. Great. And from this we learned two things. We learned the source port, which this side used, and we learned the sequence numbers that we're using. I'm going to cheat and just use these sequence numbers. The magic trick in all of this, the holy grail of doing this would be doing this without this information. And that's for a later talk. But for now, we'll just use these. So we're going to use HPIG3. We'll use base port, which is the source port 35130, which is right from here. desk port 1337. We use -M, which stands for sequence number. If you're not. And if you try to use the long option here, it actually doesn't work. I had this is M-M, sequence number. One thing I want to do first is echo a message connecting targets to TCP to say jet. Where am I? Check to. Great. So we'll do this again, and then we'll do -D, and then since I didn't bother to figure out how big that file was, this is the number of bytes it is.
Check 2.
Inject 2.
Oh yeah, thanks. That's going to be helpful. All right, inject 2. I'll inject. We'll do spoof. We don't have to do this because this is actually a legitimate IP we own, but we could do this. We're going to spoof from 127.0.0.1, and we're going to send it to 127.0.0.1. And if we do that, you can see that we actually sent a packet, and it got accepted by this TCP stack with the data that we sent from before. So yeah, so HPIC3 is a great tool. You can basically craft arbitrary packets from the command line. Another way you can do that is with dpacket and dnet, but I won't get into that today. So with that, I'll be happy to answer any questions that you guys have. And yeah, thanks. Yeah.
So is that effectively man in the middle?
So that's not a man in the middle because I cheated and used tcpdump and injected data into it. If I were able to do that without the tcpdump, that would have been called a TCP blind data injection attack. And if I was, because I was on path, I was able to see this. It's called a TCP not blind because you're on path data injection. And that's the lame version of TCP injection. The cool version is to do it blind where you're an off-path attacker. So it's like, I have a connection to Pat and someone else in this room, or better yet, someone at another university is able to inject packets into our connection without knowing other parameters, just to think about that connection. So that's an open research problem. Yeah. Any other questions? Yeah.
Where are you getting your default TTL information? Because it looks like Linux used to have like default 255 hops, and then it went down to 30, and then Windows used to have 30 and went to like 128.
Yeah. So
is there a reason that they would start out with?
So
like
if the world were perfect, we would just use twice the diameter of the internet. And in fact, that was like an RFC for a while. Was just to use twice whatever the diameter was, and at the time it was like 20. But that ended up breaking some systems, either because some people would do really stupid things on the internet, and so like packets just wouldn't get to their destination, and so then they have this incentive to just be like, well, whatever, just increase it until it works. That combined with the fact that like routing loops are pretty uncommon, and we don't really diagnose them with TTLs, and TTLs don't really save us from the damages that routing loops cause, makes it not as worth it to have a smaller TTL, because if the packet goes around 10 times instead of 5, it's not really, the marginal difference is pretty small on that router.
Why don't you use like a timestamp rather than a TTL?
That's a good question. So why not use a timestamp instead of a TTL? If you use a timestamp, then all of the hosts on the internet have to have synchronized clocks. So you all have to know what time it is. And that turns out to be a much harder problem than you would imagine on the face of it. But basically, if I ask your computer what time it is, it's probably going to disagree with my computer by order of seconds. If I ask a Windows XP machine what time it is, we might differ by days. If I ask a computer that hasn't been online in a while, it could be years.